Now the topic that we are going to talk about now is about the electric field lines. And electric field lines are actually a graphical method of encoding and decoding information about the electric field in some region in space that will give me at a glimpse a rough idea about the magnitude, the direction of the electric field, and also an idea about the types and the relative magnitudes of the charge involved if there are charges. The electric field lines look something like this if you look at them. So they are lines, and they might be straight lines in some parts, there might be curved lines, and they have arrows on these lines. Of course, we will see what does this mean, but this is roughly how they look. And now the idea behind these, if we know the rules for drawing these lines, then by a look, if you know these rules, then by a look, a single look, you can tell a lot about the electric field in this region. Now, what does this tell us? It tells us actually many things. The first thing is that when you know the electric field, you have the electric field lines in some region drawn, then you can find the direction of the electric field at some point, and this will be the tangent to the line passing through that point. So if you want to find the electric field here, you draw a tangent here, and this would be the electric field vector here. If you want to find it here, well, the tangent coincides with the line here. If you want to find the electric field vector here, then you draw a tangent here, okay, and this will be the direction of the electric field there. Also, it can give you an idea about the relative magnitude of the electric field. In other words, and how is this? Well, the number of lines per unit area through a surface, a hypothetical surface, perpendicular to the lines, is proportional to the magnitude of the electric field lines in that region. So, for example, if you look here, if you imagine a surface here and a surface here, the number of lines crossing the per unit area in this surface here is larger than it is here, and so the strength of the electric field, or the intensity, the magnitude of the electric field, is larger here than it is here. We will illustrate this first by an example. So we have this example. Of course, these surfaces do not exist. We put them, we imagine that they are. So we have these electric field lines, and we see that if we have these two surfaces that I have just talked about, a hypothetical surface, we see that the number of electric field lines that cross per unit area on this surface is larger than it is on this surface. So this tells me that the intensity of the strength of the electric field, the magnitude of the electric field on this surface is larger than it is on that surface. Well, roughly, actually, you can say it this way. You say that the density of lines, okay, whenever the relative density of line give you an idea about the magnitude of the electric field. In other words, when the lines are more densely packed, then the electric field is larger than when they are less densely packed. Of course, I'm talking about a relative thing here, okay? There is no rule saying that if you have 10 lines, then this is the magnitude of the electric field. No, it is not that way. It just gives you an idea about the relative magnitude of the electric field line. So by looking here, you say, okay, the electric field is intense here than, and it is less intense here, or the magnitude is less here, and so this is not a uniform electric field as far as magnitude is concerned. So this is, what does this tell you? Also, if you look at the direction even, you can see that if you draw tangents to the electric field lines at different points, the tangents will not be parallel. So the electric field is not pointing in the same direction all the way. So the direction of the electric field is also is not constant. So this is an electric field which doesn't have a constant magnitude and doesn't have a constant direction. So it's not a uniform electric field. For a uniform electric field, the lines, the electric field must be constant in magnitude and constant and pointing all the way, all the time in the same direction, which is not the case here. Now, let's see the rules of encoding information into the electric field line. That is, how the rules for drawing electric field lines. The first rule is that the electric field lines originate at the positive charge and terminate at negative charges. Now, if you don't have another type of charge, then in this case they will terminate at infinity, or if it's negative they will originate at infinity. Or if you have excess of one type of charge, then part of the electric field lines in this case will terminate on the originate at the positive and terminate at the negative, but part will terminate at infinity or originate from infinity if if you have excess charge. Now, the other rule is, this is important, the number of lines drawn leaving a positive charge or entering a negative charge, that's originating at a positive charge or terminating a negative charge, point charge, gives you a rough idea or relative idea about or give you an idea about the relative magnitude of these two charges. Okay, so the larger is the charge, the more electric field lines will be leaving or entering that charge. Again, this is a relative thing. There is no rule saying that if you have five lines, then leaving the charge, then this is this much coulombs. No, it is just if you have two charges and you want to show that they are different in magnitude, then the number of field lines entering or leaving these charges, actually each of these charges gives you an idea about this. No two field lines can cross. This is a very important point, because simply, as we have said, the electric field direction is tangent to the electric field lines. Now, at a given point, if you have two lines crossing at a given point, then this means that you will have two different tangents at that point, which means that you will have two different directions for the electric field at that point. But the electric field is unique in space. It has only one magnitude and one direction at each point in space. And so this is impossible. Electric field lines should not cross. And of course, we have to keep in mind that these electric field lines are just a mental picture. They are not something real, material, exist in nature. They exist only on our brains. But of course, they are just a mental tool. But it is a very useful mental tool by us. Now we will consider various examples illustrating what we have said. The first is a positive point charge and a negative point charge. Well, while these are drawn adjacent to each other here, actually they are meant to say, we are saying that we have here a positive charge that is isolated from anything else. So in the region around this positive charge, there is nothing, no other charge. Okay, the same applies for a negative charge. So what I'm talking about here, a single point positive point charge and a single point negative charge with no other charges around them, but I'm drawing them adjacent to each other on the board. So if we look at this positive point charge, then we apply the rule. We say that, okay, I know this is positive, so the electric field lines should be originating at this positive charge. And so this is the case. Now, they will be terminating at infinity because there is no other negative charge in its vicinity to terminate at, so they terminate at infinity. The second thing, they are rays, straight lines, which have directions, so they are rays in this case. Now, why is this? Well, this is because they reflect what we know about the direction of the electric field of a point charge. We know that the electric field at any point in P, for example, here of a point charge, will be always directed about r hat, which goes from the source point charge to the point P. So r hat is always in this direction. If you want to find it here, the electric field, then the electric field should point in this direction. If it is here, the electric field should be here. Not only this, all the points along this ray will have the same electric field pointing along the ray. Okay? So, and since the electric field line, the direction of the electric field vector is always tangential to the electric field line, the only way to achieve this is to draw these as rays, straight rays originating at the positive point charge. Now, the other thing is that the density of these lines, in other words, the number of lines passing per unit area on a surface perpendicular to the lines, this density drops as we go away from the charge, okay, as we get further from the charge. And this, of course, reflects that the electric field weakens. And this is what we know, because the electric field of a point charge drops as 1 over r square. It is just kq over r square. So it drops as 1 over r square. R is the distance from the charge. And therefore, we expect this, these charges to be, these lines to become less dense as we move. And this is happening symmetrically. This is important. Now, and as you can see also, one final point is that no two lines cross each other. Okay, they do not intersect. Now, if you look at the negative point charge, what we have said applies exactly, except now that these charges, these lines, originate at infinity and terminate at the negative charge, and as per our rule. And otherwise, they are, as you can see, radial, and they're also their density drops as you go away from the charge, and this drop is happens symmetrically. Now, another example of the electric field line is that of the electric field of a dipole. Dipole, as we know, consists of two equal and opposite point charges. Now, these are the electric field lines. As you can see, they originate at the positive and they terminate at the negative charge. And note that the form of the electric field lines are now different than when you have single isolated charges, because the field now in the region is not due to each charge, to a single point charge. It is the resultant field of the two charges together, and therefore this will be different than the field of a single point charge. So for example, the field here will be pointing in this direction. It is tangent to this line. The field here will be tangent to this line, will be pointing this direction. The field here at this point will be pointing this direction. They originate at the positive and they terminate at the negative. Some of them might terminate, extend to larger distances, as you can see from here. Their density varies because the electric, as you go away from the dipole, because at the end, when you go far, when you are farther from the charges, the electric field weakens because it is the sum of the electric field of two charges. Each of them drops as 1 over r square. So when you go away, the r for each of these becomes larger, and so the electric field of each of these drops, and so their resultant electric field will also drop. So as you can see, the density becomes less. The number of field lines leaving the positive charge and those entering the negative charge is the same, to indicate that these are two charges that have equal magnitudes. Now, the other example is that of two point charges which have equal magnitude and equal sign. And as you can see, in this case, since I don't have negative charges, I have only positive charges, the field lines will originate at these charges, but they will extend to infinity and they will terminate there. They don't have any other negative charge to terminate at. In the region between them here, for example, at point C, you'll have a point where you have 0 electric field, and so there are no lines here. And also, as you can see, the number of lines leaving A and leaving this charge and this charge is the same because they are of equal magnitude. Now, the other example is that of 2 point charges, one positive, one negative, but the positive charge is twice the negative charge. So, as you can see here, the number of lines leaving the positive charge is double the number of lines enter the negative charge, because it has twice the magnitude. This. Now, if you look at the trend here of the lines that are free now, because I have an excess of positive charge, so not all the charges of the lines leaving the positive charge will terminate at the negative charge. So far away, these will straighten, and you will, when you look far away, you will see only rays coming out, and so they will look like the electric field lines of a single point charge of a magnitude q minus 2q, which is plus q. Now you check this checkpoint, and also this important checkpoint where you will identify how will the electric field lines of a uniform electric field look like. This is very important thing to know and to learn.